Welcome to the world of aromatic compounds. From the sweet-smelling essential oils that gave them their name to the fundamental building blocks of pharmaceuticals, plastics, and DNA, aromatic compounds are everywhere. In this presentation, we will explore the unique stability of the benzene ring, understand why Hückel's rule defines aromaticity, learn to name benzene derivatives, discover how aromatic compounds react, and master the art of identifying aromatic molecules. Let us begin our journey into the heart of organic chemistry. In 1825, Michael Faraday isolated benzene from illuminating gas. For decades, its unusual stability and formula C6H6 puzzled chemists. Why was this compound so stable despite being highly unsaturated? The breakthrough came in 1865 when Auguste Kekulé proposed a cyclic structure after a famous dream of a snake biting its own tail. Kekulé's structure featured alternating single and double bonds in a six-membered ring. This explained benzene's stoichiometry, but not its extraordinary stability. The puzzle of benzene's resonance energy, about 152 kilojoules per mole more stable than expected, would later be resolved by quantum mechanics and the concept of delocalized pi electrons. Benzene is a planar hexagonal molecule with all 6 carbon atoms forming a regular hexagon. Each carbon is sp2 hybridized with bond angles of exactly 120 degrees. Every carbon has one p orbital perpendicular to the ring plane. These 6 p orbitals overlap sideways to form a continuous ring of pi electron density above and below the molecular plane, a delocalized pi system. Unlike Kekulé's alternating bonds, all 6 carbon-carbon bonds in benzene are exactly equal in length, 1.398 angstroms, intermediate between a single bond at 1.54 angstroms and a double bond at 1.34 angstroms, giving a bond order of 1.5. This equalization is direct experimental evidence of electron delocalization. Resonance theory describes benzene as a hybrid of 2 equivalent Kekulé structures. The true structure is not either of these, but a resonance hybrid with delocalized electrons. This delocalization, the 6 pi electrons free to move around the ring, accounts for benzene's exceptional stability. We represent this with a circle inside the hexagon. The resonance energy, approximately 152 kilojoules per mole, is the extra stabilization benzene enjoys compared to a hypothetical 1,3,5-cyclohexatrine with localized double bonds. This stabilization makes benzene much less reactive toward addition reactions than typical alkenes, instead favoring substitution reactions that preserve aromaticity. In 1931, Erich Hückel developed a quantum mechanical criterion for aromaticity. For a planar, cyclic, fully conjugated molecule to be aromatic, it must have 4n plus 2 pi electrons, where n is any integer, 0, 1, 2, 3, and so on. Benzene has 6 pi electrons, that is 4 times 1 plus 2, with n equals 1, making it aromatic. Cyclobutadiene would have 4 pi electrons, 4n with n equals 1, making it antiaromatic, highly unstable. Cyclooctatetraene has 8 pi electrons, 4n with n equals 2, but it is nonaromatic because it twists into a tub conformation to avoid antiaromaticity. This simple electron counting rule allows us to predict aromaticity in countless organic molecules. A molecule must satisfy 4 conditions to be aromatic. First, it must be cyclic, a closed loop of atoms. Second, it must be planar, all atoms in the same plane for proper p orbital overlap. Third, it must be fully conjugated. Every atom in the ring must have a p orbital available for the delocalized system. And fourth, it must have 4n plus 2 pi electrons following Hückel's rule. If a molecule satisfies the first 3 but has 4n pi electrons, it is antiaromatic, destabilized. If it fails any of the first 3 criteria, it is non-aromatic. Examples of non-aromatic molecules include cyclooctatetrene, which is not planar, and open-chain conjugated systems, which are not cyclic. Understanding these criteria is essential for predicting chemical behavior. Benzene derivatives are named by identifying substituents attached to the ring. Monosubstituted benzenes use the substituent name as a prefix. Toluene is methylbenzene, phenol is hydroxybenzene, aniline is aminobenzene, and benzoic acid is carboxybenzene. For disubstituted benzenes, the relative positions are critical: ortho for 1, 2, meta for 1, 3, and para for 1, 4. Electron-donating groups like hydroxyl and methyl are ortho-para directors. Electron-withdrawing groups like nitro and cyano are meta-directors. This directing effect is crucial for predicting products in electrophilic aromatic substitution reactions. Aromatic compounds can contain atoms other than carbon in the ring. These are heteroarenes. Pyridine has a nitrogen atom replacing one CH group in a 6-membered ring. The nitrogen's lone pair is in an sp2 orbital in the plane, not part of the pi system, so pyridine has 6 pi electrons and is aromatic. Pyrrole has a nitrogen in a 5-membered ring. Here, the nitrogen contributes its lone pair to the pi system, giving 6 pi electrons, 4 from 2 double bonds plus 2 from nitrogen. Furan and thiophene have oxygen and sulfur in 5-membered rings, similarly contributing lone pairs. These heterocycles are fundamental in pharmaceuticals, agrochemicals, and materials science. When multiple benzene rings fuse together, they form polycyclic aromatic hydrocarbons, or PAHs. Naphthalene consists of 2 fused benzene rings sharing a common carbon-carbon bond. Anthracene has 3 linearly fused rings, while phenanthrene has 3 fused rings in an angular arrangement. PAHs follow Hückel's rule for each individual ring, but also have global aromatic character. Larger PAHs like pyrene, coronene, and graphene sheets extend this concept to 2 dimensions. PAHs are formed during incomplete combustion and are found in coal, crude oil, and grilled foods. Some PAHs are known carcinogens. Despite health concerns, PAHs are also essential in organic electronics and materials science as semiconductors. The most characteristic reaction of aromatic compounds is electrophilic aromatic substitution, or EAS, where an electrophile replaces a hydrogen atom on the ring. The mechanism involves 2 steps. First, the electrophile attacks the pi system to form a resonance-stabilized arenium ion intermediate, also called the sigma complex, which is non-aromatic. The intermediate then loses a proton to restore aromaticity, a strongly favorable step. Common EAS reactions include nitration with nitric and sulfuric acid, halogenation with bromine and iron bromide, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. The regiochemistry is controlled by existing substituents. Activating groups direct ortho and para, while deactivating groups direct meta. Quiz question 1. How many pi electrons does benzene have? Option A, 4 pi electrons. Option B, 6 pi electrons. Option C, 8 pi electrons. Option D, 10 pi electrons. Take a moment to think about this before we reveal the answer. The correct answer is option B, 6 pi electrons. Benzene has 6 pi electrons, 1 from each of the 6 carbon p orbitals. This satisfies Hückel's rule. 4 times 1 plus 2 equals 6, with n equals 1. This is what makes benzene aromatic and unusually stable. Quiz question 2. What are the carbon-carbon bond lengths in benzene? Option A, 1.54 and 1.34 angstroms, alternating. Option B, all 1.54 angstroms, all single bonds. Option C, all 1.398 angstroms, all equal. Option D, all 1.20 angstroms, all triple bonds. Think carefully before the answer is revealed. The correct answer is option C. All 6 carbon-carbon bonds in benzene are exactly 1.398 angstroms, equal and intermediate between a single bond at 1.54 and a double bond at 1.34 angstroms. This bond equalization is direct evidence of electron delocalization around the ring. Quiz question 3. Which of the following is not a criterion for aromaticity? Option A, the molecule must be cyclic. Option B, the molecule must be planar. Option C, the molecule must contain a benzene ring. Option D, the molecule must have 4n plus 2 pi electrons. Consider each option carefully. The correct answer is option C. A molecule does not need to contain a benzene ring to be aromatic. Many non-benzenoid compounds are aromatic, such as pyridine, pyrrole, furan, and the cyclopropenium cation. The 4 criteria are cyclic, planar, fully conjugated, and 4n plus 2 pi electrons. Quiz question 4. Which substituent is a meta-director in electrophilic aromatic substitution? Option A, hydroxyl, O. Option B, methyl, CH3. Option C, nitro, NO2. Option D, amino, NH2. Think about the directing effects of each group. The correct answer is option C, the nitro group. The nitro group is a strong electron withdrawing group, making it a meta-director. The hydroxyl, methyl, and amino groups are all electron donating groups that direct ortho and para. Quiz question 5. How many pi electrons does the cyclopentadienyl anion have? And is it aromatic? Option A, 4 pi electrons, antiaromatic. Option B, 5 pi electrons, not fully conjugated. Option C, 6 pi electrons, aromatic. Option D, 8 pi electrons, non-aromatic. Count the pi electrons carefully. The correct answer is option C. The cyclopentadienyl anion has 6 pi electrons. The 5-membered ring with one sp3 carbon loses a proton, and that carbon becomes sp2 hybridized, contributing its lone pair to the conjugated pi system. With 6 pi electrons, 4 times 1 plus 2 with n equals 1, planar, cyclic, and fully conjugated, it is aromatic. Problem 1. Identifying aromatic compounds. Determine whether the following molecules are aromatic, antiaromatic, or nonaromatic. A. Cycloheptatrene, C7H8. B. Cycloheptatrienyl cation, C7H7+. C. Cyclopropenyl cation, C3H3+. Step 1. Analyze cycloheptatrene. Cycloheptatrene has one sp3 carbon, a CH2 group that interrupts conjugation. It is not fully conjugated, therefore it is non-aromatic. Step 2. Analyze the cycloheptatrienyl cation. Removing a hydride from the CH2 gives an sp2 cation, restoring conjugation. Now we have 3 double bonds, that is 6 pi electrons. It is planar, cyclic, and conjugated. 6 equals 4 times 1 plus 2, therefore it is aromatic. This is known as the tropylium cation. Step 3. Analyze the cyclopropenyl cation. A 3-membered ring with one double bond equals 2 pi electrons. It is planar, cyclic, fully conjugated with 2 pi electrons. 2 equals 4 times 0 plus 2, n equals 0, therefore it is aromatic. The answer? A is non-aromatic, B is aromatic, C is aromatic. Problem 2. Naming benzene derivatives. Name the following aromatic compounds. A. C6H5CH2CC. B. 1,3-dinitrobenzene. C. Cavix or fem or 3 methoxy group. D. Bromine group at para position to OH. Step 1. Identify the parent name. For part A, an ethyl group attached to a benzene ring. Simple alkyl substituent plus benzene equals ethylbenzene. Step 2. Recognize disubstituted patterns. For part B, 2 nitro groups at positions 1 and 3. 1, 3 is meta position, so meta-dinitrobenzene. Step 3. Identify functional group priority. For part C, OCH3 is methoxy group attached to benzene. This is known as anisole or methoxybenzene. Step 4. Determine numbering with multiple substituents. For part D, OH is the parent functional group, making it phenol. Bromine at position 4, para, so 4-bromophenol. The answer: A. Ethylbenzene, B. Metadinitrobenzene, C. Anisole, D. 4-bromophenol. Problem 3. Pi electron counting. Count the pi electrons in each molecule and predict aromaticity. A. Pyridine, C5H5N, B. Pyrrole, C4H5N, C. Furan, C4H4O. Step 1. Analyze pyridine. Pyridine has 3 double bonds, that is 6 pi electrons from the carbon-carbon bonds. The nitrogen lone pair is in an sp2 orbital in the plane of the ring. It is not part of the pi system. Total is 6 pi electrons, 4 times 1 plus 2, aromatic. Step 2. Analyze pyrrole. Pyrrole has 2 double bonds, 4 pi electrons from carbon-carbon bonds. The nitrogen lone pair is in a p orbital perpendicular to the ring. It is part of the pi system. So 4 plus 2 equals 6 pi electrons total. 6 equals 4 times 1 plus 2, aromatic. Step 3. Analyze furan. Furan has 2 double bonds, 4 pi electrons from carbon-carbon bonds. The oxygen atom has 2 lone pairs, one in plane and one in a p orbital. The p lone pair contributes to the pi system, giving 4 plus 2 equals 6 pi electrons. All 3 heterocycles are aromatic with 6 pi electrons. Problem 4. Predicting EAS products. Predict the major products of nitration of A. Toluene, C6H5CH3, B. Nitrobenzene, C6H5NO2. Step 1. Identify directing effects. For part A, toluene has a CH3 group which is electron donating, an ortho-para director. Electrophilic attack is favored at ortho and para positions. We get a mixture of ortho-nitrotoluene and para-nitrotoluene. The para product is often the major isomer because the ortho position is slightly sterically hindered. Step 2. Analyze nitrobenzene. The NO2 group is electron withdrawing, a meta-director. The ring is deactivated, so the reaction is slower. Electrophilic attack occurs at the meta position. The major product is meta-dinitrobenzene as a single product. The answer: A. ortho and para-nitrotoluene, B. Meta-dinitro